Well, hello everyone, and welcome to this new tutorial. So in this new Abaqus tutorial, we are going to discuss how to model damage, and specifically how to model ductile damage for metallic materials such as steel. So we're going to go through the theory and how this is defined in Abaqus, and what are the actual meaning of all the different parameters that you need to define in Abaqus. So let's start first with the damage definitions. And if I recall the previous tutorials when we discussed how to model the plasticity behavior of metals, and if you remember, for the plastic behavior, we used to define in Abaqus the true stress values versus the plastic strain values. And if you are modeling this as a nonlinear plastic behavior, so generally you input a number of data points representing the shape of the stress plastic strain behavior, similar to this one that we see over here. And of course, your initial point, this is the point of the yield stress, which starts at a plastic strain of 0 after the elastic stage. And then from this point on, the stress keeps increasing with larger strain values. The problem is that when we are trying to model something like fracture or damage in metals, we need this stress values to decrease at some point so that eventually the strength is lost in the component or the part that you are trying to model. This is why we need to define the damage definition or the damage behavior in addition to the elastic and plastic behaviors. So how do we define damage? There are two things that we need to define. We need to define the initiation of the damage. Basically, you are defining value of the plastic strain at which damage will start occurring. The next thing that you need to define is what's going on after this initiation. So once the initiation of damage took place at the specified plastic strain, then there will be some evolution in damage. This basically defines how the stress is being reduced after this point. So the true stress that you defined in the plastic behavior, how will it be reduced after this point until it reaches 0 or fails completely? Visually, this looks something like that. If you don't have damage modeled, then your stress will be this value based on your defined plastic behavior. But now, because I have the damage evolution, then your stress value will be reduced by this amount 1 minus d. D is called the damage parameter. The more that you go with the plastic deformation, the more reduction you are getting in the stress, and eventually you are going to reach the failure point. At this point, you lose your material, and then you can see fracture in your model. So what we are going to discuss today is how to define this initiation and this evolution parts. So when it comes to damage criteria, there are several types of criteria available in Abaqus. So from the material module, we discussed before how to define the elastic and plastic behaviors. If you go to the mechanical behavior, you will see that you can add damage for ductile metals, and this will give you 7 options as shown over here. These 7 options include ductile damage, shear damage, and Johnson-Cook damage criteria. And then you have 4 additional damage models. The first 3, those are what we generally use for metallic materials when we are dealing with solid and shell elements. The remaining 4, those are damage models that can be used for sheet metal instability when you are using like shell or plane stress elements. For today's tutorial, we are focusing on ductile damage criteria, but the same concepts that we are going through apply to both the shear and the Johnson-Cook models as well. So now we are talking about ductile damage criteria. As we mentioned, there are 2 things that we need to define. We need to define the initiation criteria and then the evolution function. So let's start with the damage initiation. What damage initiation means? It means that this is the initiation of loss in material stiffness. Material stiffness is the slope of the stress plastic strain curve. Currently, the slope is going upward. Okay, it's always positive. So now once we have damage, this slope will be reduced. In order for this to happen, we need to define a starting point after which this reduction in stress will occur. And as I mentioned, essentially we will be defining the strain or the plastic strain at which the damage will initiate. When we specify that, the damage parameter D, the small letter D, will have a value of 0. And the more you go in plastic strain after this point, the more the value of D will increase until it reaches 1, which means full failure. The question now is how to define this plastic strain for damage initiation. Well, in Abaqus manual, you will see that this plastic strain, or that we call it the equivalent plastic strain at the onset of damage, this is a function of stress triaxiality and the strain rate. The critical plastic strain, or the equivalent plastic strain, which is the field variable PEEQ at the onset of damage, is a function of the stress triaxiality and the plastic strain rate. For our tutorial today, we are not focusing on this parameter. We're just assuming that we are modeling things static. We don't have any strain rate dependency, so we can just ignore this parameter. So basically, we're just looking at the value of the plastic strain at damage initiation as a function of stress triaxiality. Why is this important? Why do we have stress triaxiality here? Because if I tell you what's the plastic strain at the onset of damage, if you say the plastic strain is 0.1, for example, this value does not have a clear meaning, because this 0.1 of strain can take place in a mesh element in many forms. So this 0.1 can be in compression, or it can be in tension, or it can be in shear. So the same value have a different meaning depending on the stress state that the element is subjected to. This is why we need to define this plastic strain value as a function of stress triaxiality. This stress triaxiality, called triax as the field variable, this tells Abaqus what is the stress state at the mesh element. So the stress triaxiality is computed as the ratio between the pressure stress and the von Mises stress. So this is the expression for that. So the pressure stress is the average of all the normal stresses in all the three directions. And the von Mises stress, we discussed this in previous tutorials, is computed with this formula considering all the stress components. The value of the stress triaxiality varies. If we are looking at the fundamental cases, you will get these values. The most important ones perhaps for our tutorial and when we are dealing with metals is the uniaxial tension one. If you have uniaxial tension on your mesh element, the stress triaxiality value is 1/3, and under shear the value is equal to 0. And then you have the other values over here for compression and biaxial tension, but for most things that we are dealing with, we are actually looking at those two main triaxiality values. In an actual simulation, the value of the triaxiality is not 1/3 exact because you have deformations happening in all dimensions. So in Abaqus, when you select the ductile damage, you are going to get this prompt for defining the initiation criteria. Abaqus will tell you to define the three parameters: the fracture strain and the corresponding stress triaxiality value and the corresponding strain rate. Again, if we are not modeling anything that has strain rate dependency, then this third column we can just ignore. Other than that, you just need to define the plastic strain at damage initiation and the corresponding stress triaxiality. So if we are dealing with a uniaxial tensile case like a coupon test, for example, or something like that, simply you can just assume that damage initiates once you have necking. In that case, you can just set the value of the plastic strain at the onset of damage equal to the plastic strain at the ultimate point based on your engineering stress strain behavior. You can refer to the previous tutorial about that. And you already know that because this is a uniaxial tension case, then that this corresponds to a stress triaxiality of 1/3. So I can just enter this value, whatever it is, plastic value at the ultimate point, and I specify the stress triaxiality equal to 0.333 or 1/3. And the strain rate I can just put equal to 0. So that's it. Then we defined the damage initiation criteria. Of course, in general cases, we have multi-axis loading. Not only that, even if I'm modeling tensile case, or the mesh element is deforming in the 3D space, so the stress triaxiality is not exactly 1/3. It is better in that case that you define the value of the fracture strain here at the onset of damage as a function of triaxiality for multiple values of triaxiality. So instead of adding just one row to this table, we need to add multiple rows that define the full dependency between the plastic strain value at the onset of damage and the stress triaxiality. If you just put one like this, then Abaqus will just assume that it doesn't change, that this fracture strain does not change with the stress triaxiality, and it would apply this to any triaxiality in your model. So we said what's recommended if you have like a general case, that you define this relation. So now it's not just a single point. Instead, we are defining an entire relation between the critical fracture strain and the triaxiality. This is called in the literature a fracture locus. So this relation or this curve defining the boundary for initiation of damage. In the literature, you will see different types of curves for different types of materials defined by different researchers. Those showing over here, those are the typical ones that you will find in the literature. So it looks something like this, or it looks something like that. And you will see here that in most cases, when we are dealing with metallic materials for our applications, we are concerned with the part of the curve in this region close to the shear and close to the uniaxial tension. Once you finish the definition of the damage initiation, this only tells Abaqus when does damage initiate. But if you define this and that's all, no damage will take place in your model. Actually, no change will happen in your model. So at this point, what you have defined so far, like this fracture locus and so on, is just an indicative reference that can tell you if damage occurred or did not occur in terms of status in your model, but nothing physically will change in your model. In order to see actual damage in your model, you must define the second part of the damage definition, which is the damage evolution. So this is what we are going to discuss next, how to define the damage evolution portion of your model. So the damage evolution is a sub-option of your ductile damage. So if you click on this sub-options, you will get the damage evolution, and then you will get this prompt over here. So the damage evolution can be defined in two ways. You can define as a function of the fracture energy dissipation at failure. So this is the type option from here. You can choose energy, or you can define it as displacement, which is the equivalent plastic displacement at failure. If you choose energy, you need to indicate this critical parameter GF, which is the fracture energy dissipated at failure. And if you choose displacement, you need to define this UF plastic, which is the equivalent plastic displacement at failure. Let's start with the definition based on the displacement. So here, if I choose the displacement, I need to specify two things. I need to specify the actual value of this plastic displacement, and then I need to specify the shape of the damage parameter to the plastic displacement curve. This is called the softening curve. So the softening curve here, you have three options. You can choose that this curve is linear. This means that this damage parameter changes linearly with the plastic displacement until you reach the failure displacement that you indicated here. Of course, at the failure displacement, the damage parameter will be equal to 1. So it starts at 0 and then it goes to 1 when you get complete failure. You can choose also exponential. It will look something like that. You need to specify this additional parameter alpha to define the shape of your exponential curve. Or you can just use a tabular format. In this case, you just need to specify how the value of D changes with the plastic displacement. Now let's see here what are the steps once you define this plastic displacement at failure and you define the shape of your damage parameter to the plastic failure displacement. Once you define this relation, what really happens? So what happens is, first, while you are loading your material, if I'm looking here at the stress strain curve, so once you reach the initiation point, Abaqus starts to measure any strains after this point. So this is the epsilon hat plastic over here. So once you push your material beyond the damage initiation point, then you have some additional plastic strain. Once you have this strain, Abaqus will transform this plastic strain into plastic displacement. This is done by multiplying the strain with the characteristic length of your mesh element. So what is the characteristic length of your mesh element? Let's say here that you have hexahedral element, a brick element. Any brick element has three main dimensions, L1, L2, L3. The characteristic length of your element is the length of the line joining the opposite corners of your element. So this LC indicated over here. This is the case if you are dealing with a linear element. If you are dealing with a quadratic element, LC will be half this length. You can read more about the value of the characteristic length of the element from the Abaqus documentation. If you have an element that has an aspect ratio of 1, so your elements are like cube-shaped, which is the recommended in general when you are dealing with this kind of damage simulation, then LC is the length of the element, the global size of the element that you have in your model, multiplied by square root of 3. In any case, once Abaqus computes the plastic displacement out of the plastic strain, then Abaqus goes to the softening curve that you have defined, which is the relation between the damage parameter and the plastic displacement. And then it queries the value of the damage parameter based on the current plastic displacement. Once Abaqus obtains the value of the damage parameter at the current step, then Abaqus goes back to your plastic material definition and reduces the true stress value by 1 minus d, and then you get the stress in the material, and then the equilibrium continues from this point on. So the same process keeps repeating with increasing plastic strain. Eventually, this plastic displacement is going to reach the plastic failure displacement that you already defined as part of your damage evolution definition. And at this point, the damage parameter is equal to 1, and then you are going to get total failure. You will note as well here that if you set the value of the plastic displacement at failure equal to 0, this means that right after the initiation of damage, failure will occur. Of course, you have to be careful with this kind of definition, because if you do that, this might cause some issues with conversions if you are using a static solver. In general, you want the drop in strength or stress to be gradual as possible to avoid sharp changes in the stiffness. Now, you should note here that the relation between the degraded shape of your stress plastic strain curve is the inverse of the shape of your damage parameter plastic displacement curve. This is exactly the case. This is true if you defined an elastic, perfectly plastic material, like a material that doesn't have hardening. So if you define elastic, perfectly plastic material, and you defined a linear softening curve like this one, then your stress strain behavior and similarly your global force deformation behavior will drop linearly as shown over here. So it's for the inverse of your DUF plastic shape. So this one is increasing linearly, this one is decreasing linearly. With the same thing, if you are defining this as an exponential softening curve, then your drop in strength, it will look like the inverse of this exponential shape. If you have something tabulated, arbitrary shape like this one, user-defined one like this, your stress strain behavior will look the exact opposite or the inverse of this one. If you don't have a perfectly plastic material, if you have like a hardening material with like some nonlinearity in it, then the degraded shape will still be the inverse of the softening, but it might have some additional nonlinearity. Now you can choose based on what kind of damage you want to see after the damage initiation, what kind of shape of drop in force, then you can define your softening curve shape accordingly. This is pretty much how you define the two parameters for the damage evolution based on the equivalent plastic displacement. If we are doing this using the other option, which is the energy option or GF, the same exact process to define the value of GF instead of UF plastic, and you still need to define the shape of the softening curve. The only difference is just that you are going to specify a different value here, GF instead of UF plastic. In fact, this GF is the integral of your stress U plastic curve from the point of damage initiation until the point of failure. If I have a linear degradation in my stress strain curve like this one, then GF can be computed as the area of this triangle, which is half sigma D, which is your ultimate stress or the stress at the onset of damage, multiplied by this distance, which is the effective plastic failure displacement. You can see here that GF and UF plastic are interchangeable, so you can use either this or that. No change will happen in the results. GF, based on this definition shown over here, will have a unit of Newton per millimeter or force per displacement. So you can use either of those two, it doesn't make a difference. Now, a final note here, the literature, how about these parameters? So we discussed the definition of these parameters and how to input those into Abaqus, but where can you find these parameters and this fracture locus? If you look in the literature, you will see many recommendations for defining all of these parameters and the damage evolution values. Most of these studies, they compute these parameters through calibrations with test data, and then they provide you the values that they recommend for different types of metals. Ductile damage model formulation is intended to alleviate the strong mesh dependency, but you need to be careful here because now we are talking about damage. Once the onset of damage happens, you are getting necking, you are getting strain localizations into your mesh element. So this means that the size of your mesh element affects the definition of those parameters. And you need to conduct like some mesh sensitivity analysis to make sure that your parameters are okay. Last thing is when you are defining your field variables, there are a number of key variables that you might want to save during your analysis. This includes the stress triaxiality. So this will tell you what's the actual triaxiality in your mesh elements. The second thing is the damage initiation criterion. So this is the name of the field variable. And this will tell you later on in the ODB file if a given element have reached damage initiation or did not. So it gives you a value less than 1 or 1. Less than 1 meaning that you didn't reach damage initiation at this particular element. The criteria have been reached. There is also the tensile damage variable and the stiffness degradation variable, SDEG. This is basically the D parameter that we discussed in the slides. And finally, if you want to simulate element deletion, you can select the element deletion option when you are defining your mesh. Additionally, when you are defining your field variables, you can check for this status option so that this is activated. So now let's go to Abaqus and see a quick example with a simple bowl and see how these parameters are defined and how things are simulated. Okay, so I'm here in Abaqus and I have this model already opened. This is a model of a simple bolt. It's a grade 8.8 bolt. I will not go through the drawing of the geometry of the bolt part. You can check that in the previous tutorials. What I will focus here now is the definition of the material. So if I open the material manager, I have already a material defined. Let me look at this material definition. So I have the density definition. I have the elastic behavior definition. And I have here the plastic behavior definition. This is all the exact same as what we discussed in the previous tutorials. Those values over here for the plastic values I obtained from the steel generator app. So if I open it here on the side, I just select an 8.8 steel grade and I put the values of my sigma Y and sigma ultimate and so on. And I click generate plastic data and I got the true stress strain behavior, which I pasted inside of Abaqus as you see over here. So this we already know from the previous tutorials. What's new now is that we need to add the damage definition. So I'm going to go to mechanical properties, damage for ductile metals, and I'm going to choose ductile damage. So now we have the ductile damage, and now I need to define the damage initiation criteria, which is, as we discussed before, the plastic fracture strain, the corresponding stress triaxiality. How can I obtain this? We discussed this in the slides, but I can still use the steel generator. So if I go here and I click on damage parameter, if I check this box, I just need to specify the mesh element size. So this depends on what I'm going to use here to mesh my bolt. Let's say that I'm meshing my bolts using 1 millimeter mesh size. I also need to define what is the characteristic length of my element. So I'm assuming that I'm going to mesh this using hexahedral elements that have an aspect ratio very close to 1. So my LC here, because I'm going to use linear elements, so this means that LC can be approximately computed as the mesh size multiplied by square root of 3, which gives me 1.73 millimeter. Notice here that once I change these values, automatically I have the value here for the UF being changed. This is the value of the plastic failure strain that will be used later on when we are defining the damage evolution portion of the ductile damage definition. Then I will just click on generate damage data, and I need to browse for the location of the file and select a folder to save it. Once I do that, if you go to the plot and then you select here the damage plot, you can see here this is the fracture locus that has been defined based on the data that we entered. So this data of this curve, which is the fracture strain versus the stress triaxiality, this red curve, is now available in the text file that we just generated. So I'm going to open my text file where I got the data, and then I copy the data, and then I will just paste it directly into Abaqus. All the strain rate values are put to 0 because, again, I'm not modeling anything related to a strain rate dependency. That's it. So now we have the damage initiation defined. The next thing that we need to do is to define the damage evolution. So I will click on the sub options damage evolution. I'm going to choose the displacement type. For the softening, I'm going to use tabular values. But of course, I can use linear or exponential. This depends on your own preference. No problem with that. And here, I just need now to define the damage variable D versus the plastic displacement U plastic. If I go back to my steel generator, I already know the value of UF, which is here, it's giving me 0.33. So I will start with the first point in the curve as 0. And 0, so the damage is equal to 0 when this effective plastic displacement is equal to 0. So this is at the onset of damage. I don't have any damage yet. Then when I reach 0.33 plastic displacement, I want my damage to be equal to 1. But if I do that, I could have chosen the linear definition for the softening. Instead, at 0.33, I'm going to make the damage variable equal to 0.35, which means I'm going to use 0.65 of my true stress at this point. And then I'm going to lose then the entire true stress. Once I reach a little bit, I will put just a little bit, like maybe 5% or a little bit more beyond my plastic fracture strain, so that I don't have like a very sharp sudden drop in stiffness, because as we said, this can cause some problems with conversions. So that's it. I defined here my damage evolution. The only thing that I will need to say now is okay. And now this is it. Your damage definition is done and you have your material already defined. Then if I go back to the mesh, let me check now that my mesh is consistent with my definition. So here I'm using 0.5. We said 1 when we obtained the values from the steel generator. So I'm going to apply 1 and I'm going to remesh my bolt again. So it's very important that this is consistent with the parameters that you've defined. So we have this defined. We can go here to the assign element type just to make sure that this is linear element, because this affects the characteristic length of your element if it's something else. So here, yes, this is a hexahedral element with reduced integration. It's a linear one. By the way, here I'm running explicit simulation, so I'm using elements from the explicit library. I'm doing explicit simulation because I want to simulate entire failure until the element removal of the element, and this is only feasible with the explicit solver. If you do the static solver, you are going to see the drop in strength, but you will stop short from the complete failure of your component. So for visualization, I just need to scroll here, and then you need to make sure that you are selecting element deletion option. And also for the maximum degradation, I'm specifying the value here of 0.99 instead of 1. Discuss this in the RC modeling tutorial. So now I'm done with the mesh. The next thing that you want to check is the field variables. So if I go to the field variables, I edit those. So you can see here that I'm looking at the reaction forces, I'm looking at stresses. I want to see elongations, displacement, you want to save things related to strains. You can also save strains, which is pretty much a very good thing to do, like the PEQ, the equivalent plastic strain, if you want to compare this with what you model and check how does your model is actually working in the background. And from the failure fracture field variables, I'm selecting the tensile damage parameter. I'm selecting the damage initiation criteria that will tell me if my element reached this point or not. And from the status one, I'm selecting the status option. Speaking also of stresses, perhaps it would be wise to also select the stress triaxiality over here from the drop-down menu if we want to see the actual value of stress triaxiality in your different elements. So you will see that in the beginning they are very close to 1/3 because I'm going to apply tension on the bolt. But eventually, once deformation is starting to occur, this value will deviate from 1/3. So I click OK. And here for the loading, I have 2 reference points as we used to this by now in all the tutorials. And I have this side fixed, the bolt head, and then I'm pulling this side. And I'm going to run this, and then we'll look at the results. So here I have my analysis finished, and here I'm in the ODB. And if I look here at the simulation, if I see this deformed thing, then I see here the bolt already deformed. If I play the animation, so it starts pulling, and then you get the necking, and eventually you get the damage, which results in failure at the end. So this is as expected. And if I look here, I can investigate further the values of, let's say, the stress triaxiality. So if I look at the stress triaxiality, you can see here that everything is green, which essentially very close to 0.33. So in the beginning, when I'm pulling, all the elements are experiencing stress triaxiality around this area, which is 0.33. If we want to get the exact value, we can go to Tools, Query, and I'm going to say Probe Values. And you can see here, if I'm hovering around these areas, you can see the value of stress triaxiality here in the middle. It's around 0.3 in this range, 0.31, 0.34, 0.4. So it's all very close to the 0.33 range. And this is the case all the way until you get a fracture. so you are moving in the same region. You can also look at the ductile criterion, which tells you if you have reached the damage initiation or not. So in the beginning, everything is blue. This means the damage criterion is 0. And the more you load, the value keeps increasing. But as long as the value here of the damage criterion is less than 1, this means that damage initiation did not happen yet. Now, once it goes into the red, this means it's getting into 1. This means that you have reached the damage initiation part and that damage already started based on the damage evolution that you have defined. Same thing here. If I look at the S degradation parameter, this is the D parameter, and you can see that the D parameter in the beginning is 0, the blue color. And then the more you move, eventually it reaches 1, which is the red color over here. Also, if you go to your history output, if I try to plot the force versus the displacement of the entire bolt, so I can do that using the save as option, and I can use the combine option to plot the curve while swapping the variables. If I click OK, so the curve here is like just inverted because the force value is negative, but you can see that it started from 0. Then you have the elastic part, then you have the yielding, and then you reach the top, and then you start getting the necking, and then eventually the force drops down and fracture eventually occurs. So this is all about the basics of defining ductile damage in Abaqus. Of course, there are much more information that you need to read about in the available references about the specifics of defining the fracture locus and how the mesh affects your definition. So I would recommend that you read further into this to improve your skills. Also, there are other damage criteria present that you can define. We said we just covered the ductile damage definition. There is also the shear damage criteria and the Johnson-Cook criteria. So you can define those as well. So you can define multiple criteria for the same model. Depend, of course, of how general and what kind of forces are being applied in your simulations. So you can read more about those in the Abaqus manual. But the same basics that we discussed today applies to those as well. So I hope this tutorial was helpful to you, and we'll see you in the next tutorial.